Till now, we've been discussing certain idealized models of computations. However, the real physical devices that implement such models in practice are always imperfect. In other words, during the work of computers, errors may occur. Of course, as errors occur, the total computer performance decreases. That's why different approaches to cope with errors were suggested. It is not always possible to eliminate all of the error sources in practice. However, in many cases, one could minimize the chance of their occurrence. This circumstance allows one to perform classical and quantum computations, which consist of a great number of logical operations with high efficiency. Today we will start to discuss the error correction theory. We will get familiarized with its methods, which were developed for the classical computations, and then were generalized for quantum case. So, there are three main problems in classical error correction theory, and they are interconnected with each other. The first problem is the analysis of errors occurring in the information channel and their description in terms of a mathematical model. The second problem is the error-resistant information encoding. And the third problem is the creation of error correction procedures and algorithms. Let's now discuss each of these problems separately. A very important notion of information channel is introduced in the theory of computation. This refers to any device for the transfer, storage, and processing of information. In fact, these are all changes that could happen to the information bits from the moment they are submitted to a computing device's input to the moment they are read. In other words, the information channel is the description of the bit set's evolution between two certain moments of time. If there are errors during the processing and transferring of information, then the channel is called error-free or identical. Of course, an error-free channel is the most desirable information channel for effective computations. However, if our channel is noisy, we must learn how to describe the errors occurring in the channel mathematically. This problem is of great practical value. The thing is, every information channel should be tested before any computations or information transfer. The black box test involves special testing signals being sent to the box's input, then the statistical analysis of received results is performed. This test allows one to identify and classify the errors that could occur in the channel. The latter means that the errors are described via mathematical models. Such a description allows one to select methods for an error correction. In other words, in order to correct the error, one needs a good understanding of the type of errors that he is dealing with. As an example, let's consider some standard error models. The simplest type of errors is independent single-qubit random errors that have the same probability for every bit value. This model is schematically depicted on the slide. In this model, the error occurs in a separate bit at a random moment of time. The probabilities of a bit flip are the same for both bit values 0 and 1. Thus, the probability that bit's value doesn't change is 1 minus p. The more complicated model of a single bit error includes a probability distribution for every bit value, as you can see on the picture. In this model, the error probability for a bit value of 0 is p1, and for a bit value 1, the error probability is p2. Thus, the probability of not changing for 0 value is 1 minus p1, and the probability of not changing for 1 value is 1 minus p2. The most general case includes multi-bit or correlated errors. It means that this error results in uncontrollable changes in several bits at once. Such errors are being schematically depicted by a certain logical element. You can see it on the slide depicted by the epsilon super c. The index c is for classical errors. The action of such logical element can be represented as a set of certain logical operations, which could be both single-bit or multi-bit. Each operation, epsilon I, goes with its probability pi. Of course, it's much more harder to correct correlated errors than single-bit errors, but the correction methods for these both types of errors are based on the same principles, and therefore we will further consider only single-bit errors. If one has a model of error that is the mathematical description of noise processes in the information channel, then one is able to choose the encoding methods that will make the information more resistant to this type of errors. It will help one to restore the information after an error. The information encoding is based on the redundancy principle. It means that several auxiliary bits are added to the initial ones. The initial and auxiliary bits form the so-called code words. For example, instead of a regular bit with values of 0 and 1, we can now consider a logical bit with logical values 0L and 1L. These logical values are certain code words. For a 3-bit code, which we will consider in our next lesson, the code word 0L is just the sequence of 3 zeros, and the code word 1L is the sequence of 3 ones. So, every value of the logical bits is encoded via 3 regular bits of information. We emphasize that the information redundancy corresponds to a certain error type. It means that after a part of information is corrupted because of errors, the rest part of information must be enough to restore the initial information. Going forward, we note that the channel's quality, that is the type of error that may occur, determines whether a certain encoding method can be used or not. The information encoding is depicted on the slide as a certain reversible logical element G_ENC, which acts on a set of source bits A. These are A1, A2, and so on, AN, and on a set of M auxiliary bits Z. Every auxiliary bit is in the 0 state. As a result, we obtain the code word AENC, which consists of n plus m bits. So, since we increase the number of bits for the encoding of the code word A and obtain the code word AENC, we realize the redundancy principle. As we have already said, the encoding element G_ENC is reversible. It means that there exists the inversible operation of encoding that turns the code word AENC into the source sets A and S. Let's now discuss the procedure of an error recovery. So, if there was an error, then the code word will be somehow destroyed. Instead of the AENC, we'll obtain the AR. If we apply the decoding operation to the AR, we won't obtain the source sets A and C. So we need a special decoding procedure that will allow us to restore the A bit set at least without restoring the auxiliary S bit set. Of course, it would be better to restore both A and S sets in order to manage without encoding decoding procedures for further usage of the code word. However, it is not always possible. The decoding is possible if different code words are different from each other after the affection of an error. We recall that the error affection can be considered as an action of a certain logical element on a code word. So, if we have a set of errors E sub EI, as I goes from 0 to n, which can occur in the channel, then two different code words should be different from each other. For example, if we have two code words AENC and BENC, and the errors EI and EG affected the AENC and BENC code words respectively, then for all E and G, the distort code words AR and BR should be different. In this case, all errors from the set are called correctable. We've depicted schematically the set of correctable errors that can occur if we encode the 0-bit values with 3 zeros and the 1-bit value with 3 ones. This is the so-called random single-bit error. As it occurs, no more than one bit is changed. So we have four possibilities: one when there were no errors at all, and one for an error in each of 3 bits. As can be seen, the resulting sets of code words do not coincide. So we can easily guess where was the logical 1 and where was the logical 0. So, in this case, we have enough information for the restoration procedure. In our next lesson, we will discuss the 3-bit code and its applicability limits. And that's all for now. Thank you for your attention.